Welcome to section 9.3. Now we're going to look at a specific sequence called the geometric sequence. This is technically exponential. Now we have a common ratio. If you remember, we talked about that exponential function where I said the base is sometimes known as the ratio or common ratio. There's your r right there. So here's your base, there's your power. Now, if a sequence has a common ratio between terms, which means you take the second term divided by the first, third divided by the second, fourth divided by the preceding third. It's always the term before it. So if I had the sixth term, I divide it by the fifth term. If these ratios are always equal to each other, that's your common ratio, your R. And if you have that, then you can write your geometric sequence function as a sub n equals the first term times r to the n minus 1 power. So using this formula, find the 10th term of the sequence 2, 6, 18, 54. Well, we want to find the 10th term, so that's a sub 10. Next, a sub 1 is 2. Now we look at, well, 6 divided by 2, 3. 18 divided by 6, 3. 54 divided by 18, 3. So we're always multiplying by 3. That's your R. So my formula is a sub n times 2 times 3 to the n minus 1 power. Well, we're looking for the 10th term, so we're going to put 10 in for those n's. So this is now 2 times 3 to the 9th power, which is 39,366. These numbers are going to get huge really fast because we're constantly multiplying. Find the geometric sequence function if the third term is 36 and the fifth term is 16. This one's best to describe visually like we did that other problem that had 13 terms. So the third term, 36, fifth term, 16. As we did before, instead of plus d, it's now going to be times r. Another times r to get to 16. So this is my equation, 36 times r squared, because there's two r's, equals 16. And now we solve for r. Divide over the 36, reduce it to 4/9. Take the square root of both sides, positive or negative 2/3. Since you're solving for an r squared, there's two answers. Okay, well, wait a minute. That means we have two possible geometric sequences. So since we multiplied by 2/3 to get to this number, multiplied by 2/3 to get to 16, now we work in reverse. You either divide by 2/3, or we don't divide by fractions, we multiply by its reciprocal. So 2 goes into 36 18 times, times 3 is 54. Do that again to get to your first term. Either divide by 2/3 or multiply by the reciprocals easier. 2 goes into 54 27 times. 27 times 3, 81. So there's my first term. So one equation will be a sub n equals 81 with a positive 2/3 in parentheses raised to the n minus 1 power. And the second one would be with a negative 2/3 in the parentheses. Because even if you start at 81, you multiply by a negative 2/3, then multiply by a negative again, you get a positive. Multiply by a negative to get a negative. Multiply this term by a negative, you go back to positive. So it could be either one of those. If you have an r cubed, remember there will be no plus or minus, so you just get one possible answer. Next, our geometric series is s sub n equals a sub 1 plus a sub 1 times r plus a sub 1 times r squared all the way up to a sub 1 times r to the n minus 1. So if I want to find my formula, I'm going to put a little bit more terms in here so you can see it. And what I'm looking to do is I really want to cancel out everything in the middle. So what I need is some negative terms. So what I'm technically going to do is multiply both sides of this equation by a negative r to create another equation. So negative r times s sub n, there it is. Now a sub 1 times negative r is now negative a sub 1 r. Negative r times this second term is negative a sub 1, now r squared. So what's happening up here is all my signs go from plus to minus, and all the powers on my r increase by 1. So when we get to the end, adding 1 to n minus 1 is now just n. Adding 1 to n minus 2 is now n minus 1. Well, if you look really close, opposite terms, opposite terms, opposite, 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 opposite. If I add these together, all those terms there are going to cancel. So s sub n minus r times s sub n equals the first term minus the last term of my second equation. That just got rid of a lot of terms. Now, we can go a little bit further, some more algebra. Both of these terms have a capital S sub n in. Factor it out to get 1 minus r. Over here, both these terms have an a sub 1 in it. Factor it out. Solve for s sub n. Divide over that binomial. And folks, we just went from s sub n equal to this one formula where all I need is the first term, the common ratio r, and how many terms n, and I can find the sum. So if I had to find the 10th partial sum of 5, 10, 20, 40, which means I'm just keep multiplying by 2, wait a minute, if I keep multiplying by 2, that's my r value. All right, so using this new formula, 10th partial sum is 10, that's my n, first term 5, r is 2. I have everything I need to find the sum. S sub 10 is going to equal the 2 times 1 minus 2 to the 10th power over 1 minus 2. Okay, so 1 minus 2, well, that's the tough math, that's negative 1. 2 to the 10th power is 1024. Well, take 1 away from that, you'll have a negative 1023. So a negative divided by a negative will be a positive. The 1 on the bottom's gone. 5 times 1023, 5,115. All right. Next, we're going to do something really crazy. Find the infinite sum of 1,000 plus 500 plus 250 plus 125 plus. You keep adding these. How do you keep adding out to infinity? Well, we can do that. We're just got to be manipulative. First term, a sub 1 is 1,000. Now, my numbers are getting smaller, so I'm not, well, it looks like I'm dividing by 2 or multiplying by a half. Okay, r is a half, that's good. The problem is how far do we go? We go to infinity. Put it in the formula. What? Yes, put it in the formula. S sub infinity for the n equals 1,000 minus 1, 1,000 times 1 minus 1/2 to the infinite power over 1 minus a half. Let's think about this 1/2 to the infinite power. 1 times 1 times 1 times 1 is always going to be a 1. But 2 times 2, 4, 2 times 4 is 8, 2 times 8, 16. The bottom keeps getting bigger and bigger and bigger and bigger and gargantuan until the point you have 1 over something huge like infinity means you're getting closer and closer to 0. That is cool. 1/2 to the power of infinity is going to 0. Put it in. 1 minus 0, 1 times 1,000, 1,000. 1,000 divided by a half, well, multiply by the reciprocal of 2. 1,000 times 2, 2,000. That's unreal. I can find an infinite number of numbers adding together. Exactly. The problem here is that eventually what you are going to be adding on to your existing sum is something that's so minutely small you can't tell the difference anymore. Think of it this way. Oh, let's see. I'm going to go to a place in California I've visited many times. Huntington Beach, a great surfer's paradise. Okay, I'm on the beach. They have great white sand. It's awesome. All right. If I happen to pick up 1 grain of sand and I walked off with it, would the beach know the difference? No. That's how small I'm adding 1 grain of sand to the entire beach. How many grains are there? Whatever was there before I took the 1 grain away, it's still the same. Okay? Another crazy concept using the same formula. We're going to prove that the repeating decimal 0.9999 really does equal 1. So we got to make a series. 0.9 repeating is 0.9 plus 0.09 to get now 2 nines in a row. Then 0.009, 3 nines, 0.0009, and you keep doing that forever. Okay, write them as fractions. 9 tenths, 9 100ths, 9 over 1,000, 9 over 10,000. This is a geometric series. We're going out to infinity for n, just like we did here, but now I keep multiplying by 1 over 10. 9 times 1, 9. 10 times 10, 100. 9 times 1, 9. 100 times 10, 1,000. First term 9 over 10, r 1 over 10. Put it in your formula. 9 tenths times 1 minus 1 over 10. Again, we're going to get the same thing. 1 over something huge. This is approaching 0. It's converging to 0 where it doesn't matter. Get rid of it. So 1 minus 0 is 1. Times 9 tenths is 9 tenths. 1 minus 1 tenth is 9. Get out of Dodge. 9 tenths divided by 9 tenths is 1. We just proved it. Kind of freaky, isn't it? By this concept of understanding where numbers approach, this is the bridge taking you from college algebra to calculus. All right, so we got to start bouncing and thinking outside of the box. So 0.9 repeating does equal 1. All right, so the concept we're talking about here is when a series diverge or converge. All right, the difference between these two words is as follows. If a finite sum, S of n, approaches a number, say capital L, as n goes to infinity, we say that this infinite geometric series, k equals 1 over infinity, converges. A series diverges if your sum keeps getting bigger and bigger and bigger, and it goes to positive infinity, or it keeps getting smaller and smaller and smaller to where it's approaching negative infinity. Now, how do we know when a series like this is going to converge or diverge? How do we know if we're going to this capital L value or infinity? All depends on the r. If this infinite geometric series will always converge when your r, your ratio, is somewhere between 0 and 1 when you make it a positive. All right? You could say negative 1 is less than r is less than 1, but that's not good because we don't want it to be equal to 0. So it's best to just say, let's take the absolute value of whatever the r is And if it's between 0 and 1, it converges. So now, remember how that 1 minus r to the infinity power just became a 1? We don't need this binomial anymore, so we can have what is known as a special infinite sum formula, which is the first term over 1 minus the common ratio r. And that's going to converge. If your common ratio is bigger than or equal to 1 after you take its absolute value, then it diverges. That means the sum is going to infinity. Okay? All right, so that wraps up 9.3. I'm going to put another video at next. You don't have to watch it if you have the 84 plus CE. If you have an older graphing calculator, you'll want to watch it.